So 3a, determine and characterize the zeros of f of z equals z sine z. Okay, so what the hell do they mean by determine and characterize the zeros of this function? So I mean, the zeros of a function is pretty straightforward. Like that's just the, you know, the values of z, which make f of z equal to 0. But um, what um, what do they mean by characterize? So we'll see what that means in a second. But first, let's just determine where are actually the zeros of this function, right? So okay, well, f of z will be equal to 0 if and only if, well, it's z times sine z. So it's if and only if z equals 0 or sine of z is equal to 0, right? Okay. Now, I mean, okay. So we've got z equals 0 as an obvious solution. And then whenever a sine of z is equal to 0. So as you already know well, um, for sine of x, it's got plenty of zeros, right? And those occur at the multiples of pi. And it turns out that this actually is the only places where it's 0 still. I think this can be assumed. Sorry, well, I'm talking a bit too fast. Um, in fact, yeah, like that's still the only zeros of sine z are the real when z is real and equal to a multiple of pi. Let's go through it one more time because first of all, I'm starting to doubt myself a little bit, and it's a really good thing to see. That's kind of nice that yeah, sine and cosine still have the same zeros as before, as when they were just functions of a real variable. There's no extra zeros. Okay, so f of z is equal to 0 if and only if z is a multiple of pi. Okay, so we've determined what the zeros are, but what do they mean by characterize? So, okay, so we say f of z, excuse me, we say a whole, hmm, so say a function, saying, yeah, we say a holomorphic function f from U to C. I use this open subset. So f is basically differentiable on this whole open subset. Say this a holomorphic function f from U to C has a 0 of order n at z in U if and only if, well, first of all, f of z is equal to 0. And, okay, yeah, and we have that the first derivative is also 0, and the second derivative is also 0. And every derivative up to the n minus first derivative is 0, but the nth derivative is not 0. Yeah, at least that's the definition I was given in this course. Um, uh, an alternative, an alternative definition is that the Taylor series expansion of uh, uh, this Taylor series expansion of f z at, maybe let me call it z naught actually throughout, has a 0 of order n at z naught. F of z naught is 0 and the derivatives are 0, but the nth derivative is not 0. At z naught has the form, basically, it starts off with a term of order n. Right? So that's equivalent to these conditions there. Okay, I mean, but the derivatives are like pretty straightforward to check. Um, I suppose sometimes one definition is like a little bit more convenient than the other, but I mean the derivatives are usually pretty easy to check. Oh wow, what have I? Huh, where have I gone? There we are. Okay, so remember that f of z was this function here. Um, so I mean, I already have a bit of an intuition as to what's going to happen because you see, obviously, when z equals 0, then we have a 0 of order 1 from z, and it turns out like all of the zeros of sine z are of order 1. Okay, that's a good thing to kind of keep in mind. And so a 0 of order 1 times a 0 of order 1 should give you a 0 of order 2 at z equals 0. While for the other ones, at other multiples of pi, pi, 2 pi, etc., then we get a 0 of order 1 here and we don't get a 0 here. So that should give us a 0 of order 1. But we can just do the derivatives and check. So f prime z equals um, using the product rule, sine z plus z cos z, right? All those derivative rules and standard derivatives still apply. And I'll also need the second, no, let's do the second derivative. So that'll give us cos z, and then here plus cos z minus z sine z. All right, so 2 cos z minus z sine z. Right. Well then, um, well then, if z is equal to 0, and let's call it z naught, uh, we have obviously f of z. Okay, we determine it's 0 already, so that f of z naught is 0. And what about f prime of z naught? So f prime of z naught will be equal to sine of naught plus naught times cos of naught. That's going to give us naught, right? So the order of that 0 is at least bigger than 1. And let's check the second derivative. So we'd have 2 cos naught minus naught sine naught. So that's going to give us 2, right? Which is, of course, non-zero, right? So f, just f, has a 0 of order 2 at z naught equals naught. If z naught is equal to k pi, where k is not 0, then f prime of z naught, well, let's see, it's equal to sine k pi plus k pi cos k pi, which, well, that's 0, but then cos of k pi is like plus or minus 1. So that's plus or minus k pi. In any case, it's non-zero, all right? So f has a 0 of order 1 at z naught equals k pi for each k in z, and k non-zero, right? Hmm. Okay. All right, let's finish off question 3 and then take a little break. Using the above, characterize the singularities of 1 over z sine z, and determine the non-trivial coefficients Cn for n strictly less than 1 of the Laurent expansion uh, for z between 0 and delta, where delta greater than naught is some sufficiently small constant. Hint, let g of z equals z cubed over 3 factorial minus z to the, should be z to the 5. So, oh, z squared. Oh, sorry. Z squared over 3 factorial. Okay. I see. Z squared over 3 factorial minus z 4 over 5 factorial, etc. You may assume 1 minus g to negative 1 equals 1 plus g squared, etc. is valid for mod z between 0 and delta. Okay, this is quite a heavy kind of problem statement. So let's just kind of, try and think kind of intuitively about what we're trying to do. So we want to characterize the singularities of now, maybe shall we call it not gz, because they use g. Well, let's call it f of z, okay? F of z be 1 over z sine z. All right. So this will have singularities, right? So singularity means someplace that f is not not differentiable, maybe not holomorphic, I suppose. I'm not actually quite sure. In practice, in these kinds of introductory complex analysis modules, what it means to be to have a singularity is essentially is dividing by 0 every time, right? And so this will have singularities whenever the denominator is 0, and we've we've determined that the zeros are, k pi. So F has singularities um, at z equals k pi, where k is any integer. So it has there. So, but what do they mean by characterize the singularities? Well, just like zeros, singularities, we can assign an order of a singularity, right? Um, yeah. So I think I'm gonna need to write down quite a few theorems. So, conclusion is that has a pole of order 2 at z equals 0, and a pole of order 1 at z equals k pi, where uh, k is in z and k is not 0. Well, it's z naught. By the way, poles of order 1, we call them simple poles. Okay, so so we've determined, we characterize the singularities, um, the types of singularities, a pole of order 2 at 0, a pole of order 1 at other multiples of pi. But they want more. They want to determine the non. Basically, they want the Laurent expansion centered around 0, right? Because they want the Laurent expansion in the set mod z between 0 and delta. So that's, there's the origin here. There's 0, and then, but 0 removed. And yeah, well, that's basically that's a punctured disk, right, of some radius delta, centered around 0. So they want a Laurent expansion centered around 0 for this function. So how are we going to do this? Well, 1 over z is fine, because so a Laurent expansion around 0 will be in powers of z simply, right? 'Cause z minus z naught, now it's just z. Um, so 1 over z is kind of already in the correct form. So it's 1 over sine z that we need to kind of worry about. And what they're suggesting is to use the essentially to use like what they call like the sum of a geometric series. Well, just simply the geometric series. So it's very, it's used all the time in in this module, but generally very important. So to add up 1 plus z squared and so on, add up a geometric progression, that gives you 1 over 1 minus z, provided that the modulus of z is less than 1. Okay, so what there's okay, so how are we going to make it look like a 1 minus z? Um, well, let's introduce a 1, kind of like by magic, and then let's take it away. Ooh, sorry. No, take it, yeah. And then let's take it away. So I'll write it 1 minus sine z like this. There. So I've done nothing. I've just added and taken away 1 in its denominator. But now it looks like this. I mean, it looks something like that, but where instead of z, I have this 1 minus sine z. So as long as 1 minus sine z is in size less than 1, then we can use this expansion. And so they're kind of granting us that we can assume that as long that there exists a delta small enough so that if z is in size less than delta, then 1 minus sine z is in size less than 1. So basically, in this domain, we can use the expansion. And the other thing that they're suggesting us to do is, well, what should I do? Do you know what? Actually, let me actually just use the expansion there, and then we'll use the other thing later. So that'll be 1 plus 1 minus sine z plus 1 minus sine z squared, etc., etc. And now what they're suggesting is, well, we want this in powers of um z. Ah, okay, wait. Ooh, sorry. Ah, sorry. No, no, that's not gonna, sorry, that's not gonna work. That's not gonna work because I was thinking, you know, uh, replacing sine z with its Taylor expansion. The problem with that is that what we'll get is we'll get a Taylor series, if I'm not mistaken. Uh, one. Yeah, we'll get a Taylor series, not a Laurent series. So we need to we need to work this a little differently. Let me delete that. Let me let me first actually replace sine of z with its um Taylor series, which is valid for all z, absolutely all z. So sine of z is really by definition a Taylor, Taylor series centered around 0, and it's this one, 1 minus z cubed over 3 factorial plus z to the 5 over 5 factorial minus blah 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 blah, something like that. Hmm. Okay. Now, from their hint, I see g of z is z squared over 3 factorial and so on. So, hmm. So I mean, this should have a pole of order two. So it looks like they wait. Oh, I'm sorry. I'm sorry. This is not one. This is Z. Okay, okay. Ah, I don't know why I had this. I was yeah, I had this stuck in my head. Okay, yeah, sorry. This is Z minus Z cubed as 3 factorial plus Z to the 5 factorial. Okay. So now what they do is they take a Z. Okay, now that makes more sense. So they take a Z out of the bottom to get 1 over Z squared at the front, and then 1 minus Z squared over 3 factorial plus Z to the 4 over 5 factorial minus blah, 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 blah. Okay. Mm. Um, cool. So now this is like what they call G of Z in their in their hint, right? So we'll use this geometric series up there applied to uh well, let's see. If we put brackets around here, we need to flip the signs, something like that. Yeah, so that's their G of Z. So that's 1 plus Z squared over 3 factorial minus Z to the 4 over 5 factorial and so on, plus blah, blah, blah. And then we'll have the same squared, that thing squared and so on, which looks like a big mess, but not to worry because um, we only, the question only kind of asks for the coefficients of the Laurent expansion, which for n strictly less than 1. So that means like the constant terms and the negative power terms. Um, so yeah, which is fine because you'll see that here we'll have we'll have a 1 and then we'll have a Z squared, a Z to the 4, and so on, a Z to the 6. From this, we'll only get the if you imagine like squaring this, then the smallest possible power of Z we'll have from this bracket is Z to the 4, which if combined with a 1 over Z squared is going to give us Z squared. So it's not gonna feature in it's not gonna affect the coefficients that we're interested in. And then for the cubes and so on, it's even worse. It'll only give us it'll only affect the positive powers. So that means I can just write 1 over Z squared plus 1 over 3 factorial plus blah blah blah. We don't care. The rest is just we'll have Z squared and things like that, right? But they were only interested in those, right? So essentially, um, the conclusion is that C would have, for n strictly less than 1, Cn is equal to, well, let's see, 0 if n is actually strictly less than 2. It's 1 if n equals, oh, sorry, strictly less than -2. If n equals -2, and it's 1 over 3 factorial, if n is equal to 0. Yeah. oh, I should say, if n is strictly less than -2, or of course n is equal to -1. The negative first power is, oh, the coefficient of the negative first power is 0. Oops, sorry. All right, let's take a pause. All right, we're back. So, done with question 3. Let's look at question 4. Oops.